Very good. Thank you. Better now? I hope. Great. So unfortunately, I was only recapping stuff, but I hope it's on now. Great. So where were we? So you start going through this list here. You start from the top, and if you if you've used position, or for example, if you're on a map and you want to visualize something on a map, then you can't really freely choose position, right? Then you might do something like choosing a 2D area, because like you can draw a bubble on top of a map, right? That's kind of like the restriction that you have there. And so basically pick wisely from this list. And for categorical attributes, we have the same principle here. Spatial region, which is kind of like position again, is the most efficient way to even like communicate categories. But then you can also use color hue. Motion is kind of tricky, right, in practice, but you probably want to use shape if you can't use color. So it's for example okay to have like a diamond and the little circle in a scatterplot to distinguish two categories. We talked about this example. I'm not going to go into too much detail now, but now I want to talk a little bit about the characteristics of these different channels. And so this is kind of like a formal way of thinking about them, right? The first question that we can ask is, each of these channels, is it selective? So can we say something is distinct from another mark? And so, for example, if I have 2 points in a scatterplot, they're clearly distinct, right? They're a different position, hence they're different. But if I have 2 colors, and one is light red and the other one is like medium red, then it might be hard to distinguish them, right? So these are not particularly selective. Associative is about what it supports grouping, right? So things that cluster together spatially are nicely grouped, for example, but I don't know whether things that are red and green group nicely together, right? And then is it a quantitative measure? Like basically this is asking quantity, is it a magnitude versus an identity channel? Can we quantify the difference between 2 marks? So something is not only identity, right, but also how much of a difference is there? Then we ask as well for order. Can we see a change in order if we have certain items sorted? And then the length is here, means how many distinct items can I create, right? So for example, in color, we know that we can really only distinguish 10 different colors in like most visualizations. So the length here is fairly small. Whereas in position, if I have a high resolution screen, I probably have like 1,000 different positions available on my screen, right? Even in just one dimension. Okay, so let's review them. So position, as I mentioned before, is the strongest visual variable, and it's also suitable for all data types. It is kind of like a yes to all of those attributes here. So it is selective, it's associative, it's quantitative, it has like it's ordered, and it has like a fairly big length. But of course, the problem is that sometimes it's not available. So sometimes, for example, in a map, I can't actually use position to plot my like numerical data that I want to plot, right? Because I've already used it before. And the other thing that can happen is it can lead to cluttering. So for example, if I have a scatterplot and some regions of the scatterplot are super dense, then I get a lot of overplotting, right? And so I can I have to do something smarter about this when I want to use positioning. And so like our traditional example for positional encoding is of course the scatterplot. This here is a scatterplot that also shows you some kind of like lines here that show you kind of like how much is this far away from equality. This is like men's median weekly earnings on the x-axis versus women's median weekly earnings on the y-axis. And obviously, like you see in this, like what really stands out in this chart is that basically in almost no profession do women make more than men, right? Almost everywhere men make more. And how much more is kind of like the distance here from this position to that next line, right? So here, this is like the line from where women make 10% less, and this is the line where women make 30% less, right? And so you can click on this if you want to. The slides are already up on the website, and you can like inspect those different elements. So here, positional encoding, very effective, of course. The problem with position is it works in 2D. Like the naive assumption would be, well, if it works well in 2D, why doesn't it work in 3D, right? And so the problem is that 3D on a screen is still only 2D. And so you get all of these problems with clutter. But then to really do 3D perception, you also have to do things like lighting, and that changes kind of the color perception of things. And then you have like unwanted exclusions, and the occlusions can be tricky depending on the perspective of the camera. And then labeling gets tricky, right? So 3D is really tricky. Now somebody might say, well, but then let's just use AR and VR, right? And that's maybe a solution. It probably makes some of the things better, but you still have problems of occlusion even in 3D. So, but you have stereo perception. So like in 2D, like a 2D representation of a 3D plot like this, it's really hard to tell. Like, anybody can tell me what the value of this point here is? Probably not, right? It's almost impossible to read. And that's easy to do in a scatter plot, but it also would be difficult to read that particular value in, let's say, an AR or VR headset. So length and size are good for 1D. So basically 1D are things like bars or length of a line. They're okay for 2D, like squares and circles, and they're really bad for 3D. Like, we tend to completely underestimate volume, right? And it's easy to see whether one is bigger. Like, align bars are the special case that use, as I already mentioned last time, redundantly the position of the top of the bar. So if they're aligned, you're really using position, right? But if they're not aligned, you're using length. And if you look at these attributes, like all of these are yeses, and the length is high, but maybe not as high as for position. I've shown this figure before. This is like we've had this similar encodings today on top of maps, but here is an example of an encoding from the New York Times. This is like essentially the size of different kind of like areas of spending by the government. And so you see that, like, here, these large ones, well, if I clicked on it, I would go to the New York Times website, which I don't want to do. But these are essentially Social Security and Medicare, these like big spending items, right? Okay, value, luminance, saturation are okay for quantitative data when length and size are used, but we tend to not be able to recognize all that many shapes. So they're kind of like, the length here is limited, and it's also like slightly tricky in terms of like reading quantitative problems. Remember the lecture on perception when I showed you all of these issues, that if neighboring colors influence each other, like our perception of where things are at the top or at the bottom influence each other, right? So value and luminance and saturation are reasonable if you have to use them, but they're not necessarily the best choice. This here is like this deep dive map into like voting data by the New York Times as well. Here we have like a diverging value scale, and you can see like the Democratic versus the Republican Party, what was their share. So like, I've selected the neighborhood where I live, which had like less than 1,000 people vote, and it seems to be very democratic, but not quite as democratic as downtown Salt Lake City, for example, right? So I can read this fairly reasonably from a chart like this. We'll talk more about these kinds of things in maps, of course. We talked a good deal about color already. Color is good for qualitative data. This is a 10 channel. We have this limited number of classes, so like 7 to 10 approximately, but it doesn't really work for quantitative data unless you have a legend and you would like want to like very carefully highlight certain items. There's lots of pitfalls. Be careful, use it sparingly. And I mentioned this before. My rule here is to minimize color use for encoding data and use it for brushing, for pop out, to highlight the things that I really care about, that I want you to pay attention to, right? In terms of the attributes, it is not quantitative and it's not ordered, right? Like, green isn't lower than blue naturally. Like, that doesn't make any sense. And because we have only 7 to 10 classes, it's also of limited length. Here's kind of like a tricky example. You see a lot of these in weather applications. This is estimated fraction of precipitation lost to evapotranspiration. So basically, how much of your water is like being lost to like hot weather and the water being evaporated. And we have these kind of like very intricate bands, right? So here we have 0.1 to 0.19. And then here we suddenly have like a fairly like strong change, right? If, for example, a value like up here, if a value would be 0.39, it would be violet. But if it's 0.4, it would suddenly be blue, right? So this introduces like these hard gradients, which might be kind of weird to do. Still, scientists tend to use those sometimes because it gives you this like high resolution, right? And sometimes these color maps are also learned, and so they will immediately know what's going on here. But for like, at least for general public visualization, I would refrain from doing something like this. And this was an example that I showed in a very intro class. Here we have like one color. That one color has one meaning, right? These are the players, the football players that are still active. And so that's very easy to distinguish, very simple, makes sense, easy to draw, no perceptual problems, a good use of color. There's this really amazing blog post by Lisa Charlotte Moot. She works for a data visualization company. They built this this tool that lots of journalism outlets nowadays use. And she really dives into which color maps work for what. This is really absolutely a recommended reading. Take a look at it. It's well written. It is very nuanced. It goes into details about diverging color scales, about categorical color scales, about numerical color scales, and so on. And even like when I read it, I still learned something, right? There's like lots of smart stuff that she says in this particular blog post. It's actually a series of 4 different blog posts, but they're not too long. Like you should be done in half an hour if you read all 4 of them. So the next variable here is shape. Shape is great to recognize many classes, but it doesn't do anything like grouping or ordering, right? So we can't say circle is smaller than, like a pentagon is smaller than a triangle, right? They are selective. Their associativeness is limited. They're not quantitative. They don't have an order. But one thing they have is they have like huge length, right? So we've all know many of those symbols, right? I can come up with very complex shapes. Every alphabet has different letters, right? We recognize those shapes. We need to learn them, but we can distinguish them readily, right? Especially once we learn them. So there's like many, many different options, but of course in practice, it is tricky. And people have thought, well, can't we just use shapes, especially of faces, to encode data? This is like actually an example of a very early data visualization by a Harvard statistics professor, like 60s or 70s. And the theory that he had is human beings are kind of like evolutionary trained to recognize faces, right? So we can tell apart whether somebody has narrow eyes or wide eyes, or like is smiling or not. And so the theory was, let's just take these attributes of a face and take a data vector and encode them. And so, for example, now let's suppose we have, data like grades in the school that you had as a student, right? So if you had a good grade, the eyebrows here would be narrow. If you had a bad grade, the eyebrows would be wide. And then if you excelled at like a 100-meter run, you would be frowning, right? If you like were slow at a 100-meter run, you would be smiling, right? So this would be kind of the idea behind Chernoff Faces. So what do you think? I see some people shaking heads, right? So it encodes the data, right? But it doesn't really make it readable, right? Like we would have to like really understand in depth what each parameter means, right? So clearly this is not a great visualization. So we can't really do something like this. Here I have a link to a tool that, like what the little exercise we did at the very beginning. This guy came up with 45 ways to communicate different 2 different values, right? And so you will see that some of these values, some of these ideas we came up as well, but there's some that are more out there, right? And so this is really just like an exercise and like what you can do. This one here is interesting. This is fat fonts. I think I have a slide or so later about map visualization, but this here essentially encodes a number also by its appearance. So like a 7 is very dark, and a 9 is even darker, like heavier, and thereby encoding its value as well. So, so one thing that you could ask is, well, why is this, like, what is going on? Why is volume or area so much more difficult for us to perceive than like the distance between 2 points on a map, for example, or on a chart? And it turns out there is like a law of perception that underlies all of this. This is called Stephen's psychophysical power law. And what he kind of like measured is the physical intensity of a stimulus, like how bright is something, how big does it appear, versus how we perceive it, right? And so he did like a large series of experiments with many different people. And he gave them different like charts or different stimuli, let's put it this way. And then he asked them how much is it different, right? And then he came up with these laws here. And the thing to note about this chart here is that there's only really one single line that is linear. And that one line is length. So that's basically why position and length are actually good. And everything else isn't quite as good. And so we tend to underestimate brightness, and we tend to underestimate area and depth. We tend to overestimate saturation. And like this was a psychologist, so he didn't just study charts, but he studied everything like heaviness and smell. He also studied electric shock. And so if you ever attempted to use electric shock for a data visualization, you should not, because we tend to overestimate it, right? But yeah, so this is kind of like the reason behind why these things are different, right? That this is like very like reproducible across human beings. We know that we tend to over or underestimate everything except for length. And so you have this stimulus is I to the power of n, and n is the value. And so here's the original chart that's from one of his papers. This is from 1961, and you see heaviness and taste and loudness and volume and so on, all of those sensations being shown here. Okay, I think I will wrap up here, and then I'll see you all back on Thursday, and don't forget to come when Max is talking about design on Tuesday. Thanks, everyone.